Staphylococcus aureus is a strain of pathogen that can be found almost everywhere, even on the skin or in the nose of healthy individuals. According to reports, Staphylococcus aureus infects roughly 20 to 50 individuals per 100,000 people each year, with around 10 to 30% of these individuals dying, a far more significant number than the death rates caused by AIDS, tuberculosis, and viral hepatitis combined. Moreover, due to the improper usage of antibiotics, treating staph infection is becoming more and more challenging since this strain has acquired resistance to various antibiotics. As a result, there is a noticeable increase in the amount of hospitalizations, treatment failures, or even death.
However,
the solution can be found right here.
Is an environment that holds unparalleled bacterial diversity, ranking highest among all other compartments on Earth. Why? Because it provides all required conditions for bacteria to grow, such as moisture, air, nutrients, and organic matter. Because of that, our goal is to find bacteria which has the antibacterial activity against Staphylococcus aureus. So we have a soil sample right here. Where can we do our experiments? This is the place where our experiments will be done. This is where we get our equipment. There are four main missions of our project. Firstly, we will isolate the bacterial strains with antimicrobial activity against S. aureus from 3 soil samples at Lawrence School. Secondly, we will survey the growth and resistance to S. aureus from isolated bacterial strains. The third mission is identify bacterial strains with antimicrobial activity against S. aureus. And the last one is to compare zones of inhibition between isolated bacterial strains with 3 types of antibiotic, namely tetracycline, streptomycin, and chlorpheniramine.
According to some research, the optimal pH level for the growth of Staphylococcus aureus ranges from 4.5 to 9.3. In addition, the said pathogen is also a relatively weak competitor when compared to other bacteria, and the pH levels of 3 soil samples ranged from 6 to 6.5. Based on the evidence presented above, we expect that the microorganism found in soil samples collected at LSDS will possess antagonist activity against S. aureus, with the inhibitory zones reaching around 15 to 30 mm in the diameter. Our research method can be summarized in this diagram. There are 7 main steps, then we will present each steps of our experiments. Step 1. Weigh 1 gram of each soil sample and soak in 9 ml of sterile distilled water. Each soil samples were diluted at 5 dilutions. Add 1 ml Staphylococcus aureus solution to 3 dilutions, 10 to the power of -3, 10 to the power of -4, and 10 to the power of -5. Of the 3 dilutions, take 0.5 ml from each dilution of each soil sample and spread on TSA plates. The plates were incubated at room temperature for 24 hours. This is the result that we got after 24 hours. 8 strains of bacteria were observed to have the antagonistic properties against S. aureus. The mentioned 8 strains are named after the L- syntax before being re-inoculated in TSA plates. Step 2. After selecting bacterial strains by the crew approach, the 8 bacterial isolates were chosen to undergo further examination for their antibacterial activity against S. aureus through this diffusion method on TSA plates. The picture shows the result of testing antimicrobial activity against the S. aureus of L01, L02, L03, and L04 by this diffusion method. The picture shows the result of testing antimicrobial activity against the S. aureus of L05, L06, L07, and L08 by this diffusion method. We can see that the L01, L02, and L07 shows the strongest antagonistic activity to S areas. Particularly, the average diameter of inhibitory zones against S areas produced by L01, L02, and L07 were 26.3 mm, 7.7 mm, and 15.3 mm. Step 3. Visual observation and gram staining were used to characterize the morphology of L01, L02, and L07. All three bacterial isolates were found to have a white external appearance and belongs to the Bacilli class. The test also revealed that L01 and L02 were gram-positive bacteria, while L07 was a gram-negative bacteria. Step 4. L01, L02, and L07 isolates were incubated in test tubes filled with 10 ml of TSP at room temperature. The growth of the three strains of bacteria was recorded over 10 hours, with each measurement spaced 2 hours apart. According to the provided graph, it's clear that the bacterial isolates has experienced varying degrees of growth within the 10 hours period. The application was recorded in the test tubes containing L01 after 1 hour, L02 after 45 minutes, and L07 after 80 minutes. L01 entered the static phase in the 6th to 10th hours, L07 in the 8th to the 10th hours, while during this time, L02 still continued to reproduce. Step 5. Isolates of L01 and L02 were delivered to Namqua Biotech Company for genomic DNA extraction. The 16 rRNA sequence of L01 and L02 was then subjected to NCBI Plus. The Plus results showed that the sequence of L01 gene fragments share 100% similarity with the available database sequence of Bacillus cephalosporin strain U17-1. And the sequence of L02 gene fragments share 99.97% similarity with the available database sequence of Bacillus cereus strain HD1.4b. The picture shows the phylogenetic reconstruction of Bacillus cephalosporin strain U17-1. Step 6. Given its outstanding antibacterial activity against S. aureus, L01 antagonistic property was further investigated by comparing its efficacy to numerous antibiotics, including tetracycline, streptomycin, and chloramphenicol. This diffusion test results indicated that L01 had antibacterial activity equivalent to chloramphenicol, stronger than streptomycin, and weaker than tetracycline.
The unbridled use of antibiotics has created conditions that allowed pathogens to adapt, evolve, and acquire resistance to the medicine. As a result, the development of innovative, safe, and effective antibiotics is becoming increasingly important. Through our research, L01, or Bacillus cephalosporin, was found to have the most potent antibacterial activity against Staphylococcus aureus. Furthermore, this strain also requires the least amount of time to reproduce and is relatively safe for humans, according to several studies. These results advocate that the microbial isolates from this strain can be used commercially for the production of antibiotics for staph infection after purification and proper standardization.